Okay, we're going to continue on here and finish up chapter 18, I believe. So last time we talked about batteries, we talked about a little bit of corrosion. We also talked about the Nernst equation. Um, Looks something like this, perhaps. And remember that we do sort of Nernst equation when we're sort of looking for the voltage under non-standard conditions. And again, that is basically looking at a lot of times the molarity, or if it's pressures, the pressures being that. So again, if the molarity is not 1 molar, even if the molarities are the same, like for example in our lab, they're not 1 molar, so they're not under standard conditions. So you should still use the Nernst equation to figure out the cell voltage. Pressure there, 1 atmosphere. If it's not, then also sort of our Nernst equation. And usually 25 degrees is the other sort of thing that's sort of standard conditions. So we could see how the cell voltage is affected by, say, concentration. We also talked a little bit about the idea that, you could kind of think of it almost as like a Le Chatelier's principle type situation. Again, if you have, say, a higher concentration on one side versus the other, say over here, it would sort of encourage, say, the forward direction to occur. And in that case, that would probably increase the voltage in that case, as you would be going, obviously, from, say, reactants to products. And vice versa, if you sort of were opposite there, you would kind of shift it the other way, where the reactions sort of stay together, would it be sort of occur, and probably you would see a decrease there in the voltage. So you could kind of look at it in terms of, sort of Le Chatelier's principle. In lab, we also talked about the concentration cell. And again, a concentration cell is a cell where you basically have the same anode and cathode, like say in our lab there, copper ions, basically. And again, in a sort of concentration cell, what allows the electrons to go, say, from our anode to our cathode. And under normal standard conditions, our E of our cell would equal 0 volt, as obviously our anode and cathode are the same. It is the difference in the concentration. So to say we have like 0.1 molar here and 1 molar over here. With this higher concentration, as we talked about there, you're going to have a greater positive sort of charge happening there in the solution there. That's going to allow that force needed to sort of draw the electrons to the other side. In this sort of situation, sort of flow from the lower concentration to the higher concentration in an effort to sort of equilibrate or equalize sort of the concentrations on each side. So it's that sort of concentration difference in a concentration cell that allows you to get some type of voltage that's going to occur. Um, any questions on that type of stuff there? All right, so we just have one last little topic here to talk about, and that's the idea of electrolysis. And electrolysis is a process where we use electrical energy to basically cause a non-spontaneous process to occur. And example of that would be, for example, what we see here, if we wanted to kind of break down sodium chloride into sort of its components, sodium and, say, chlorine gas in this particular case. And a little balancing, I guess, would be good as well. And in this particular situation here, we could use an electrical current, like a battery, to basically break apart, say, sodium chloride. As you may know, sodium chloride is a ionic compound that's held together by very strong electrostatic forces, and you could heat the heck out of sodium chloride, and it pretty much will just start to melt before it'll kind of break apart or into gas or anything like that. And so we need some type of chemical process here where we run an electrical current through it to get that process basically to occur. Now, when we do this, it is different than putting it together. So what I mean by that is if we were going to put this guy together in a more synthesis or combination reaction and make the sodium chloride, when we look at what's happening, like we imagine our sodium is 0, our chlorine is 0, it is +1 and -1. So once again here, when we look at is it being oxidized or reduced, and we look at the sodium, it's going from 0 to +1. It is being oxidized like we would expect since it's a metal. The chlorine here is starting at 0 and ending at -1, and it is being reduced. So in this case, we would expect, like we would normally think about it, the electrons being transferred from our metal, which are typically the guys that will give up the electrons, and our nonmetals are the guys that will accept the electrons. That means in this case, our sodium would be our anode, and our chlorine here would be our cathode in the case of sort of a galvanic cell situation. But when we are actually starting with the sodium chloride and we're sort of returning it through, say, a decomposition reaction here back into its elements, we're actually doing the opposite sort of process here. We're starting with sodium that has a +1 charge and chlorine that has a -1 charge, and we're ending with zeros for each of them. That means in our sort of electrolysis situation, we are starting with sodium at +1 and it's ending at 0. So the sodium here is actually being reduced, and the chlorine is starting at -1 and ending at 0, which it's actually being oxidized. So going in the reverse direction here, which is what we're doing in electrolysis, it is actually the sodium that is our cathode, and it is our chlorine that is our anode. So it is sort of the opposite, because it's pretty much the opposite direction of what's happening here. And that's what we see down here. We actually see our oxidation side here happening, and it is our chloride that is losing a couple of electrons and coming back to chlorine gas coming out. And on the reduction side, it is the sodium ions that are going to gain those electrons and end up here, in this case, as sodium, sort of liquid sodium metal coming out in this electrolysis sort of event. So you could do the electrolysis by adding some type of electrical energy to break apart something that normally doesn't happen. And again, sodium chloride, like I said, it normally does not break back apart unless you do some type of chemical change, which is what this is. You could also do the electrolysis of water. You can run an electrical current through water, a simple 9-volt battery, a little electrodes, and you could break apart water. Usually you need to make the water a little bit acidic, and that's why you oftentimes will see this dilute high sulfuric acid solution. Kind of just beefs up the hydrogen ions that are in the solution here and makes it work a little bit better. And in this particular case, again, we're going backwards here. So we're going from water and we're breaking it into hydrogen gas and oxygen gas in this particular case. And put two there, and that should do. And in this particular case, we are starting with hydrogen as +1, oxygen is -2, hydrogen gas and oxygen gas are both in their standard states, which means they have oxidation states of 0. So what we're actually seeing here again is in terms of hydrogen, it is starting at +1, which is here, and it's ending at 0, which means it is being reduced. And oxygen is starting at -2, heading towards 0, and it is being oxidized in this case. Again, opposite of what's happening when you put water together from hydrogen and oxygen. Those guys are flipped around. So again, we see on our oxidation here, oxygen, hydrogen going from, right, oxygen going from, come here, -2 to 0. And hydrogen here going from +1 to basically 0 over here. We see it start to bubble as we do this, and you could collect it into some test tubes over here, and we see this empty spot is not really in the empty spot. That is the hydrogen gas being collected in there. That is also the oxygen gas is being collected in there. Why is there more hydrogen gas than oxygen gas? It is H2O, right? So twice oxygen, hydrogen per oxygen, right? So you get twice as much sort of hydrogen gas collected than you do oxygen gas in this particular case. Now, I will say out of all the things that maybe you come across in terms of a electrolysis type problem. The electrolysis of water is sometimes not just told to you in blinking lights that this is the electrolysis of water. A lot of times they might not even mention it in the actual problem, but they will mention, like I said, something to do with like an acid, sulfuric acid, electrolysis of a sulfuric acid solution. So something like that is probably indicating that it's talking about the electrolysis of water. So if you see that, you're like, I'm not really sure, what it is. If some type of acid solution, and that's kind of all they mention, is probably water, and these half reactions would be the half reactions that you would want to use in that particular case. Any questions on that there? Now, when we do electrolysis problems, there's a couple of different sort of situations or ways to work these problems. But in a lot of situations, they will kind of tell you, hey, you ran this electrolysis cell at a certain current or amperage, and a coulomb is equal to an amp over times a second, not over a second, but times a second. So you could use this relationship since a lot of times they will give you sort of the current in amperage. Amperage is equal to a coulomb per second. So that's an important sort of relationship. So a lot of times, like I said, they will give you like, hey, we ran this thing for a certain amount of amperage for a certain amount of hours, say like 5 hours or something like that. You know, how much of this metal are you going to produce, or how much of this, whatever it may be, are you going to get out of this cell? So, because of that, a lot of times the time that they give you is usually in hours. You might want to get it to seconds. And usually, the start of these sort of electrolysis problems is after you convert your times into seconds, you then will multiply it by the amperage, which is basically coulombs per second. The seconds will cancel and it'll give you coulombs. This is where you're able to then use our guy here, Faraday's constant, to go from coulombs of charge to moles of electrons. So at that point, you basically could use Faraday's constant like we've used before, and this will give you moles of electrons in this case. And it's at this point that it kind of depends on the problem that you're looking at. And the deal is, this is where the half reactions are going to come into place. So if you look at a half reaction, you'll have electrons on one side, electrons on the other side, and you really could do like a mole to mole relationship, just like you would do in stoichiometry, moles of electrons to say moles of the metal you're interested in. So let's just say we had in this particular case some sodium, and it did a little bit of that. Now, if we were interested in how much sodium we would be, say, producing, we would want to go to the half reaction here, and we could see that for every 1 mole of electrons, we get 1 mole of sodium. And we could use that like a stoichiometry sort of relationship where we could take our moles of electrons in this case and convert it into moles of sodium in my example. Now that I have moles of sodium, I can use something like the molar mass to figure out how many grams of sodium I would actually produce. So this is a very common sort of pathway. You could do it for the other element that's there in the other half reaction as well, the moles of electrons to moles of that element. And you can use the molar mass from the periodic table to figure out how many grams you're going to actually produce as you let this cell sort of run for however long you run for. Any questions on that? Now, as we saw, though, for example, in the case of water, we actually produce gases. And a lot of times when we produce something like a gas, we may not be interested in how many grams of the gas that we produced, but we are sometimes interested perhaps in how much volume of a gas. And that means that sometimes in these problems, throw back a little PV equals nRT action happening. We actually could use the ideal gas law here, and we could use the ideal gas law and solve for volume, nRT over P. and figure out how much volume we would produce of this gas. Obviously, in this case, we would need to know the temperature and the pressure. The moles would come from our calculation, like over here, and we could go into the ideal gas law or something like that and solve for the volume of a gas. A reminder, right, when you use the ideal gas law, atmospheres, right, for pressure, liters for volume, moles, and our temperature there is Kelvin. Also a reminder, right, R in this case is this number, not the one we've been using like with energy, right? So make sure you use the right R if you go in there. So I would say those are two common sort of ending parts of this calculation is you figure out the moles of your elements and then you use molar mass to get grams. Or again, if it's a gas, you got some other information like temperature and pressures, you could go into the ideal gas law and solve for volume. Any questions on that there? A sort of alternative type question is sometimes they may just tell you, for example, how much you produced of an element or something like that. And maybe want to know, how long did you run the cell for? Or, what was the amperage you ran the cell for? So it's sort of the same calculation, just working backwards is sort of a variation of this type of problem. Any questions on that there? All right, so let's take a look at one here together. We'll come back to this one, I think. We'll take a look at this one. And we want to know how much calcium would be produced in this cell if we ran it at a current of 0.452 amperage and we passed it through the cell for 1.5 hours. So reminder here that we are starting in this case with the calcium chloride, and we are going to break it back apart into calcium and chlorine in this case. And in this particular case, we see calcium going from I'm sorry, not zero, going from +2 to 0. And our chloride going from -1 to 0 in this case. So again, in this situation, it is the calcium that's going from +2 to 0. Sorry, calcium going from +2 to 0 and being reduced in this case. And again, our chloride starting at -1 and heading to 0 and is being oxidized. So for our half reactions, it would be our calcium that is gaining a couple of electrons here and going to make calcium on the other side. And for our other one there, it is a couple of chlorides that is going to lose some electrons on the other side. And we're going to something like this here. Any questions on that there? All right, so these are our half reactions. And once again, this is sort of our cathode reaction in this case. This would be our anode reaction in this case. So now we know that we're going to run this cell basically at 0.452 amperage, and that is basically the same as 0.452 coulombs per second, as that's basically what an amp equals, a coulomb per second. We're also going to run it for 1.5 hours. I do want to convert my time into seconds so everything cancels out correctly. So in an hour, there's 3,600 seconds, and that is 1.5 times 3,600, about 5,400 seconds. So what I'm going to do is take the time I ran the cell for, which is 5,400 seconds. I'm going to times it by the amperage at which I ran the cell for, 0.452 coulombs per second. The seconds here are going to cancel out, and that's going to get me 2440.8 coulombs. It's at this point I'm going to use Faraday's constant to convert this into moles of electrons. So again, that is the 96,500 coulombs per mole of electron. They will cancel. And that is going to get me there 0.0253 moles of electrons. Any questions so far in the calculation? In this particular example, we're interested in our friend calcium here. So we'll go to calcium's half reaction, and I can see for every 1 mole of calcium, I have 2 moles of electrons. So just like stoichiometry, 1 mole of calcium gives me 2 moles of electrons. I'm going to use that to get me to moles of calcium. So 2 moles of electrons and 1 mole of calcium in this case. So we'll take that divided by 2. Going to give us a 0.0126 moles of calcium. In this particular case, we're looking for how many grams. So we could go to the periodic table and get the molar mass there of calcium, which should be 4008, I believe. Moles of calcium will cancel, and that's going to hit us with about 0.507 grams of calcium. So basically, if I ran this cell at that amperage for 1.5 hours, I should basically have out there about a half a gram there of calcium should come out. Any questions on that calculation there? Now, if I was also interested in chlorine, I could really pick it up from here and do the same thing. The relationship between chlorine and the electrons, which in this case happens to be a similar relationship. 1 mole of Cl2 gives me 2 moles of electrons. That would actually give me pretty much the same deal here. Give me 0.0126 moles of chlorine in this case. I could use the molar mass and again figure out how many grams of chlorine. Maybe if I had some temperature and pressure information, I could use something like the ideal gas law and figure out how much volume of chlorine as well. Any questions? All right, then why don't you try this one here and see what you come up with. We're going to a current of 1.26 amperage is passed through electrolysis cell containing sulfuric acid for 7.44 hours. Write the half cell reactions and calculate the volume of gases that's generated at STP. Once again, there is no mention of water here, but there's that sulfuric acid mentioned. So we are doing the electrolysis of water here in this particular problem. By the way, STP being standard temperature and pressure. That's a temperature of like 273 Kelvin, right? And a pressure of 1 atmosphere. Yeah. So why don't you calculate the volume of each of these? I'll give you the half reactions on the next page. So 126,744, 1.26 and 7.44 hours, I think. That's what we're running, right? And add STP. All right, so let me just give you the equations there. All right, so give it a go. We want to know how much hydrogen gas volume and how much volume of oxygen gas would we collect to this cell. Okay, let's take a look and see. So again, like I mentioned before, with the water one, sometimes they don't like kind of mention it is water. So again, look for that sort of acid, sulfuric acid type solution. But we're going to approach the same way. They did give us really the current at which we're running it at, how long we're running it at. We just want to get everybody into the right units. And mainly here, it's really our time. We just need to get it to seconds so everything cancels out correctly. So if we do that there again, there's 3,600 seconds in an hour, and that's going to get us something like 7.44 times 3,600, about 26,784 seconds. Remember that this is the same as a coulomb per second, as that is what an amperage equals, and we're going to use that basically to get our charge here, and that's going to be seconds are going to cancel, and we will end up there with about 3,374.7.84 coulombs. This is where we use Faraday's constant to get it to moles of electrons, so we can then use our half reactions. And again, we're just going to divide really by Faraday's constant. And that will get us into where we need to be in terms of electrons. And we got something like 0.34972 moles of electrons. Any questions up to that point? Now, since we're looking for both gases, we do have to actually sort of go to both half reactions here to figure it out. So we'll start with the top one here, which is our anode, and that is our oxygen. And looking at this one here, we can see that for every 1 mole of oxygen gas, we got about 4 moles of electrons. We could also look at our cathode there, and we could see there is a 4 on the outside. So if we multiply the 4 into everybody, that's going to give us something like 2 moles of hydrogen gas there. Will get us 4 moles of electrons, or you could obviously reduce it down to 1 to 2 as well, which obviously is the same sort of relationship. So you could do either one there. Any questions on how we got those? All right, so we will then do, we'll take a look at oxygen here first, perhaps, and figure out our moles of oxygen. And our moles of oxygen then would be taking our moles of electrons, using our half reaction relationship there for oxygen. 1 mole of oxygen is 4 moles of electrons. The moles of electrons are going to cancel, and that's going to get me something like 0.0874. I'll take it to one more, 3 moles of oxygen. Might as well grab our hydrogen moles as well. So starting again with our moles of electrons, using our relationship there. And in this case, like I said, 1 to 2 or 2 to 4, whichever way you want to do it. And that will get us, looks like 0.17486 moles of hydrogen. Now that I have my moles of hydrogen and oxygen, I obviously have my temperature, I have my pressure. R is a constant, which we always have. That means we pretty much have everything we need to go into our PV equals nRT. And again here, I'm going to do it for each gas separately. So solving for volume of oxygen would be and obviously we're going to divide that to the other side. Would get us our moles of oxygen, 0.08743. Our gas constant, our temperature, which is 273 Kelvin, and our pressure here, which is 1 atmosphere. Everything is going to cancel out except for liters. So that will get us here 0.08743 times 0.08206 times 273. And we'll go with a 1.96 liters of oxygen in this particular case. We're going to do pretty much the identical calculation here for hydrogen, except we're going to use hydrogen's moles. So in this case, that would be 0.34972 moles. No, it would not. It would be the other number there that actually says hydrogen. That's pretty good. Try that again. It is hydrogen. There it is. 0.17486 moles. Still our gas constant. Still 273 Kelvin. All divided by our 1 atmosphere. Once again, everything canceling out except for liters. And that is going to get us there 0.17486 times 0.08206 and 273. And that'll get us a 3.92 liters of hydrogen, which is a 2 to 1 relationship between those two, which is good as well. First off, any questions on that calculation? Yes. No, it would need to be given to you. Are you asking would it always be assumed to be STP? No. So they may actually give you some numbers and stuff like that. Now, because it happened to be STP in this case, although we did use the ideal gas law as you see there, and it worked perfectly fine. There is another way that you could solve it, as you might remember from gas, which is 1 mole of any gas is equal to 22.414 liters at STP. So if you remember that relationship, you could have just picked up with the moles here of, say, hydrogen. You could do it for the oxygen as well. And you could have just used that relationship there, that a mole is 22.414 liters, and that'll get you your same 3.92 liters of hydrogen. So because this happens to be at STP, you could use that relationship without using the ideal gas law to get to your volume. Also a reminder though, again, this is only should be used if it is at STP. So if it's not at STP, you should not use that relationship. You should definitely use the ideal gas law. And as you can see, a good reminder that even at STP conditions, you can still use the ideal gas law, just put the numbers in as well. Any questions on that? So like I said, a variation of this is something like they might tell you how much you produce and kind of work your way backwards to figure out how long you ran it for, what was the amperage, that type of deal. Any question on electrolysis here? All right, that wraps up this chapter, I think. Okay, we're gonna pick up here with chapter 19 and a reminder then non-exam material. So what we just finished is the last little bit that was on the exam, which I think we agreed upon next Thursday. We're gonna shoot with that exam. Then we'll go through obviously 18. So I think it's 17, 18, I think, if I'm not mistaken. Or 16 and 18. I don't remember what chapter are. 16, 17. That's even better. All right, so we'll go 16 and 17. That'll work. Now we're hopefully on 19, I hope, which is transition metals and coordination compounds. The majority of this chapter is about coordination compounds and complex ions. At the beginning here, we're just going to talk a little bit about transition metals, just review a couple things about transition metals, as a majority of complex ions have transition metals sort of in the center. And as we'll talk about, basically a complex ion is a metal ion that's attached to a bunch of what are referred to as ligands. And a lot of times what's in the middle there is some type of transition metal. So let's talk a little bit about transition metals, and hopefully some of this should be reviewed for you from Chem 50. But one thing we'll talk about is effective nuclear charge, and that's sometimes referred to as Z effective. And if you're not familiar with what that is, it's really the idea of the positive charge that electrons feel from the nucleus. And for example, if we took somebody like lithium, which has 3 electrons, 1s2, 2s1 in terms of its electron configuration. Basically, it has 3 protons, which means its nucleus has a positive 3 charge on the first energy level, which is what that means, right? N equals 1. There's a couple of electrons flying around. On the second energy level, there's its valence electron, right? The outermost electron sort of flying around as well. Now, when we think about sort of the attractive forces and these different types of electrons, as you may know, these are sometimes what are referred to as core electrons, which are the ones that are closest to the nucleus. These guys are valence electrons, which are outermost electrons that are involved in bonding. When we look at sort of these core electrons, because they are pretty much very close to the nucleus, they're going to feel really the sort of full brunt of that positive 3 charge that's coming off the nucleus. And one thing about sort of electrostatic attraction, which is opposites attract positive and negative charges, is the strength of that charge sort of increases with size of it. So, like a +3, -3 attraction is going to be much stronger than, say, a +1, -1 sort of attraction. So these guys are feeling really the sort of full brunt of that positive 3 charge. That is why they are held really tightly, and that is why they're not really involved in bonding, because they're really tightly held close to the nucleus. Now, when we get to, for example, here in lithium, our valence electron, which is out here floating around, obviously moving randomly about, it does not actually feel the full brunt of that positive 3 charge because it experiences what is sometimes referred to as shielding. And it is shielded from that full positive 3 charge by those lower energy electrons. So, like, when you go to movies, you sit in the middle and, movie's about to start. Somebody sits in front of you with a big hat, shields half the screen from you. You're not getting the full view. Same idea here. It's not feeling the full sort of charge. You actually calculate Z effective by basically taking the positive charge of the nucleus or protons minus the number of electrons that are shielding, which is 2 in this case. And effectively, what that outside electron is feeling in terms of a positive charge or attraction to the nucleus is actually more just like a +1 sort of attraction, which is not as strong, obviously, as a +3 attraction, which means it's not going to be held as tightly because of that. And that's also why this is our valence electron that will go off and sort of participate in bonding when lithium is involved. So all sort of valence electrons and outer electrons, they do experience some type of shielding and this Z effective sort of situation. On the periodic table, Z effective in a sense increases as you go up and to the right, sort of decreases as you go down and to the left. As you go up and to the right on the periodic table, or just to the right on the periodic table, the atomic number increases, which means there's a lot more positive protons in the nucleus. You're going to create a bigger sort of pull that's going to happen in this case. So we could see that sodium here, magnesium, aluminum, and silicon, this is going across period 3 on the periodic table. So this is going across period 3. And we can see that the effective nuclear charge increases as we go across. So because of that larger positive charge, even those outer electrons, as you go up and to the right on the periodic table, feel a stronger attraction than those guys to the left. And that's what also makes, as you go up and to the right, everybody gets smaller because of that positive charge. It just brings everybody, even the outer electrons, in closer to the nucleus. And that's why the overall size decreases as you go to the right and up on the periodic table because of that. Any questions on that? And that's what we see here as the effective increases as you go up and to the right and decreases as you go down, and a direct relationship again because of the greater effective positive charge for even those outer electrons. They're going to be pulled closer to the nucleus, and the overall size of the atom is going to get smaller. Now, a majority of what we're going to talk about in this chapter is transition metals. And just in case you forgot where they are at on the periodic table, they are between groups 2 and 3 on the periodic table there. This is the transition metals right here, sometimes referred to as the first row transition metals, right? And on the bottom here, these are sometimes referred to as inner transition metals because technically they should go right about there on the periodic table, although we don't do too much with that. Also on the periodic table, right, we have our configuration blocks. This is the S block, right, which has 2 electrons, 1 and 2. From groups 3 through 8, that is our P block, which has 6 electrons, 1, 2, 3, 4, 5, 6. If you filled up the P subshell. This is our D block, right? And that has 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And down here is our F block, which has 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So you can't count off electron configuration from the periodic table if you know what you're doing. Again, that's sodium. That is period 1, 2, 3, 4, 5, 6, and 7. So if you did something like to sodium, that would be 1s2 there, 2s2, 2p6 all the way across, and 3s1. If you came over to say chlorine over here, That would then be 3s2, 3p, 1, 2, 3, 4, and 5 if you're counting. When we get to something like transition metals, you do have to be careful because that would be 1s2, 2s2, 2p6, 3s2, 3p6. That's 4s2. As you probably know, D's start on what energy level? The third, yeah. So that's actually 3D. It is one behind the period number. That's 4D, 5D, and so forth as you go down here. Also, when you get down here, F start at 4, right? So that's 4F and 5F down here, which are 2 behind the period numbers when you look at it. So that's one way that you could do electron configuration. If you remember, S's orbitals could hold 2 maximum electrons, right? P subshell is 6, our D subshell is 10, our F subshell is 14. Perhaps you learned this little zigzag guy, 1s, 2p, 3d, 4f, and you just kind of put the numbers underneath it. And you just keep zigzagging around, right? And that gives you the correct electron configuration order, right? So that's probably a good way to do it versus, say, counting off the periodic table, unless you really do know what you're doing. And you can recreate that, by the way, just like I did there, if you not remember how, because S is start on the first energy level, P start on the second, D start and F start on the fourth. You just kind of draw it down there and just fill in the numbers underneath. You'll have the correct order in terms of electron configuration. Now, when we talk about transition metals, they do give very similarities as you go across a period or even in a given group. When they form ionic compounds, as we know from perhaps nomenclature, they do have different oxidation states. And a lot of times we have to use Roman numerals, right, when we name those guys. Cations are often complex ions. So these are transition metals that are surrounded by a number of ligands, which are Lewis bases. And Lewis bases are things that do what? Lewis means like electrons, yeah. And they actually will donate a pair of electrons. So a Lewis base is something that will donate a pair of electrons. We talked about it, I think, with the acid base chapter there. And that makes sense because if you think about your metal ion, which is a transition metal, it has a positive charge, which means it's electron deficient, which means it's actually a good Lewis acid. And our ligands here say something like water is a good Lewis base. If you remember when we did like the hydrolysis one where we had like copper with all the 6 waters, or the whatever the other one was, maybe that was there with so many waters. Those are complex ions. We oftentimes don't write the water in there. We just put aqueous next to them, but they are surrounded by these waters and stuff like that. And water is a very good Lewis base, as it has non-bonding electrons there and is polar, which allows them to be sort of donated. And that's what we see here. We have our cobalt in the middle. Ammonia, also a good Lewis base there. And that's because when we look at ammonia, it looks something like this. Also polar, also has those non-bonding electrons on the nitrogen. That's going to allow it to bond in there really well. So we get this guy right here, which is a complex ion. And before the chapter's done, you will know how to name it. And you'll be able to call it something like hexamine cobalt 3 ion or something like that, give or take name. We'll see the names. They'll just go on for days, just long, long names all the way across, which is why most people refer to it as that thing. That thing. The name's like 5 miles long. All right, but when we talk about ionic compounds with transition metals, most of them do have some different colors associated with them, as they will absorb visible light at specific wavelengths. Many of these compounds are paramagnetic. Paramagnetic means unpaired electrons, yes, heading in opposite same direction. Diamagnetic means they're paired up, right, in those spins. Good review, I like it. So when we look at electron configuration, we can write obviously electron configuration for, especially the first row transition metals, where we get into the d orbitals. As you might also be familiar with, there are a number of exceptions in the transition metal region in terms of electron configuration. And two that most people are responsible to remember are chromium and copper. And the deal here is when the electrons go into the atom, the electrons do go in. For example, if we look at chromium, which is 24, and you just wrote the electron configuration following that zigzag thing or whatever it may be, you might be tempted to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. The exception is here. It's been found that it's more stable with one extra electron up into the d orbitals and one less electron in the s orbitals. When it does come in, it comes in like this. And these energies of these orbitals are really close to begin with, so it's not a lot of energy for that extra electron to go up there. What that actually does is you look at it, there is, it fills the d orbital with electrons each. We also maximize parallel spin, which is Hund's rule, which is a really stable sort of configuration that occurs. And that is what we see here with chromium. It should have one less electron in the s, one more electron in the d. Copper as well has a similar sort of exception. And if you look on the periodic table where chromium and copper sit, and you go below and kind of in, there's a ton of exceptions just like that. Silver's an exception. PD's an exception. It has no electrons in the s. They've all been promoted up to the P. So there's a lot of exceptions right there in the transition metal region, actually underneath chromium and copper, and just kind of going in. You'll have a number of those electrons. Another really important thing in terms of electrons and transition metals is hopefully you know that when we do start, for example, filling up the d orbitals with some electrons, there's actually a switch in energy that occurs. And what ends up happening once the d orbitals get filled is the 4s orbitals actually end up higher in energy than the d orbitals. And that's really important in terms of how transition metals lose electrons. Transition metals lose electrons by losing their s electrons first. And then if they needed to dig into like another one, then they would go into the d electrons. So when they do lose electrons, that is sort of what happens. They will lose those electrons first to d, and then they will dig in and they'll lose the s's first, and then dig in and take any type of d. So if we looked at, for example, we looked at something like iron, which is 26 there. Its electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 1, 2, 3, 4, 5, 6, 3d6. So if we look at how the electrons go into iron here, they do go in like this, and then obviously we fill up our D's with some electrons. Now, as this happens, we do get this switch in the energy. level here. And our Ds do become lower in energy than our S's. So when iron becomes iron with a +2 charge, it is 24 electrons. It is these 4s electrons that actually get lost. And its configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Or again, this is argon's configuration. So you could do the shorthand of argon 3d6. All right. Now, when iron goes to a +3 situation, that is going to be 23 electrons, which means it will still lose these first, but now it has to jump into the D here, and we will end up with argon 3d5 here as its proper electron configuration. So one thing that's different about transition metals is, unlike representative metals, they actually do not end up back at noble gas configuration. Things like potassium, magnesium, when they lose electrons, they back up to a noble gas. They do not here in our transition metal region. So here we can see with Ti, and it becomes +3, it's going to lose these two first, and then it's going to take one of those electrons out, and we'll make this argon 3d1. Also, in terms of valence electrons, when we talk about transition metals, it is still equal to the group number, and it is the big group number there. So when we look at our transition, let's find that right here. There we go. It is sort of this numbering here where we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 in terms of its valence electrons. So if we looked at something like iron that we just looked at, which was argon 4s2, 3d6, that is the 8 valence electrons, as it is number 8 right there that it has available to use. It may not use them all, obviously, but that is what we look at in terms of valence electrons for our transition metals. Same thing there with our chromium that we saw, argon 4s1, 3d5, 5 and 1 is 6, chromium group number 6. So that is in terms of the valence electrons availability for transition metals, although we never get anything with like a +12 charge or anything like that. But it does have those available to them. Any questions on that there? So why don't you write the electron configuration for, we'll do, why don't we do nickel with a +4 charge? And nickel by itself is 28. Excuse me. Okay, so let's take a look. So nickel, no charge at 28 should give you something like argon 4s2, 3d8, I believe in that case. And that means that with a +4 charge, it should have 24 electrons. So we do need to get rid of 2 from there. Going to grab 2 out of there, and that would give us something like argon 3d6. Any questions on that? So it's really important for you to understand how to write electron configuration for transition metals, especially transition metals with charges, as later on in the chapter here, you'll need to figure out how many electrons they have available to them and their d orbitals to use for a particular situation. So make sure, again, that you do understand how to do that. Any questions on that? Okay. So again, talking about some other these transition metals sort of properties, and we can see oxidation state as we talked about, as we saw in that experiment we just did, the different oxidation states of Mn that we looked at, for example, different colors that we saw. I would say in that first row transition metals, mostly 3s and 2s are very common. That sort of peak up in terms of transition, in terms of oxidation state. and sort of drops back down as you come across. Now, ionization energy is the energy that's required to remove an electron in the gas state of an atom. And overall, ionization energy increases as you go up and to the right and decreases as you go down. When we talk about ionization energy, we usually are referring to really like the formation of cations, which are positively charged, since those are the ones that will lose electrons. As you may know, electrons do again come off one at a time. They don't all just drop off, at once. So, for example, magnesium, the first thing that would happen is magnesium would lose an electron. And that would be what is referred to as the first ionization energy. And the first ionization energy is basically that energy to remove the first electron. Then magnesium with a +1 charge would drop a second electron, and that would be known as the second ionization energy. And perhaps then this guy would drop another electron, and that would be our third ionization energy, and so forth. And as it continues to lose electrons, is it easier to remove the first electron or the second one? Which one is easier to do? It is the first one is much easier. It's neutral. What happens when you remove an electron is the overall size of that ion then shrinks because the electron cloud gets smaller. That means the outer electrons now have moved closer to the nucleus. It's going to feel a stronger positive charge towards that nucleus and can be held tighter. So the general trend that we see between, say, first ionization energy, second ionization energy, third, fourth, and so forth is it does increase every time you take off an electron because the size gets smaller and smaller. Those electrons that remain are now closer and closer to the nucleus and held a lot tighter. Going to take a lot more energy to do that. And we see that if we look at this is the first ionization energy, second, third, fourth, fifth, and so forth. And if we look at magnesium, it's about 735 to remove the first one. Then it roughly kind of doubles there to remove the second one, which means it is getting harder. But then as we go and jump into the third electron, it goes up by like a factor of 6 to 7-fold. And it doesn't necessarily happen. And that's because when we look at magnesium, which is 1s2, 2s2, 2p6, 3s2, it has two valence electrons. And after you pull out those two valence electrons, you're now jumping into core electrons, which is way closer to the nucleus. And good luck trying to do that. And that's why this doesn't usually happen. And that's why magnesium will basically make a +2 charge, because you hit those core electrons and you're not going to energy efficient to be able to remove those electrons. And we see that, for example, here in aluminum, first electron 580, gets a little bit harder, 1800, then 2700. But after you get rid of all three of the valence electrons there for aluminum, you jump all the way up to about 11,000 to try to remove one of those core electrons. And again, not going to really happen at that point, which again is why something like aluminum will make a +3 charge. So overall trend, ionization energy increases as you go up and to the right, decreases as you go down, gets harder and harder, and increases as you go from the first to the second to the third ionization energy. Here are some properties of transition metals. Some of these things we just talked about here. We see overall atomic radius decreases as you go to the right. We also see common charges, oxidation states, +2s and +3s. We also do see sort of a increase in density as you go to the right as well. Here's our difference between first and third, and a big jump in energy as you try to remove that third electron versus that first electron. Another one in case you missed the second ionization energy in between, but again, we see the trend there. Electron affinity is the energy change that occurs when somebody gains an electron. So we oftentimes think about electron affinity with anion formation, which are negatively guised charge. In general, the trend is it increases as you go up and to the right, decreases as you go down. It's not like a perfect trend, as you can see here with group 7, sort of increases as you go up, then kind of decreases back down a little bit, but it's not perfect. But electron affinity is different again than electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. Electron affinity is actually the energy change that occurs when it actually does gain an electron. So they are kind of two different things. Affinity you can think of, right, is you have affinity for something, you like something. So somebody has a high electron affinity and likes to gain electrons, right? So, and that's what we see as we go up and to the right as well. Electronegativity also increases up and to the right and decreases as you go down, with fluorine being our most electronegative element that there is. This is a table of our transition metals here and abilities of them to basically reduce. So reducing ability increases here. So this guy is most likely going to be oxidized, right? Because if you have ability to reduce something, it will be oxidized. And you may say to yourself, that's a pretty positive number versus this guy, right? Which is negative. This guy most likely will be reduced. And you might say, didn't we talk about like the more positive guy being the one that would be reduced? And we did. And the difference is in this case, these are all what type of reactions? These are all oxidation reactions. These are not SRP reactions, which is reduction reaction. This is sometimes referred to as standard oxidation potential. And what we see here is opposite of what we talk about when we do a SRP. If we turn all these guys into SRP values, we would reverse these reactions and the signs of all these guys would change, which means these guys would all be negatives all the way down. And then this guy would be positive, which now matches what we know, that the guy with the more positive SRP value there should be the guy that gets reduced. And the guy with the more negative SRP value would be the guy that gets oxidized in that case. So it is the same thing as what we talked about before, but we're looking at the oxidation part of it. And again, the one with more positive SOP would be oxidized, and the guy more negative would be reduced in this case. All right, here's what each of these look like in our first row transition metals, in case you have to identify them. This is a bunch of stuff that you don't have to worry about anymore. All right, so that was a little bit about transition metals, and again, it's to set the basis for sort of some of the things we're going to talk about here in the rest of this chapter, which deals a lot with transition metals being involved. So let's get into some of that, and that is coordination compounds. And when we talk about a coordination compound, it is basically has two parts to it. A coordination compound, you could kind of think of it almost like an ionic compound. There's like a positive guy and a negative guy. And when it has consists of a complex ion and a counter ion. So because it's kind of like an ionic compound, you could have a complex ion that is positive, and to balance it out, the counter ion would be negative. And vice versa, you could have a counter ion that's negative and a complex ion. I just did that backwards. A counter ion that's positive and a complex ion that's negative. That would be different. There you go. So they could be either way. And just like kind of a normal ionic compound, when we deal with coordination chemistry and coordination compounds, we always do the positive guy first and then the negative guy. So just kind of like a normal ionic guy, positive and negative. And like I said, in some of your cases, first guy may just be the counter ion, really there to balance out the charge. And the second guy could be the complex ion or vice versa. So what is a complex ion? As I mentioned earlier, it is a metal ion, and a lot of times, again, this is going to be a transition metal that's bonded to one or more molecules or ions. And again, these guys are what are known as ligands. And as we talked about there, they are Lewis bases, which means that they do have at least one pair of unshared electrons that they can donate. So as we just saw there, with water, it's got those electrons there on the oxygen that it can donate. The nitrogen here. What are things that are really good ligands or Lewis bases? Well, in order to donate electrons, you probably need an excess amount of electrons. So things that have negative charges usually mean that they have gained electrons. So they got excess amount of electrons maybe to donate. So those also make pretty good things. So our chloride ion, for example, is a good ligand as it has a negative charge. It's able to kind of donate those electrons. Now, they donate these electrons to the metal, and we really think about sort of coordination compounds like this are really complex ions in a sense, as more like our Lewis acid base combination that's happening. So remember, as we talked about there, Lewis acid is a electron acceptor, and a Lewis base is an electron pair donor. So that's sort of what we think about how the relationship sort of works in a complex ion between the ligands and the metal ions. The metal ions being that electron deficient, which is why they're positively charged, right? The only way to become positively charged is you have to lose electrons, which means you're electron deficient. So they're able to gain electrons from our Lewis bases that have excess electrons that they're able to sort of donate. So that's sort of the relationship of what a complex ion sort of thought of is as this sort of Lewis acid base combination. Now, when we look at a ligand, they are not all necessarily the same in terms of how they interact with the metal. There are certain atoms that are on the ligand that are donor atoms. So, for example, here the nitrogen and the oxygen are considered donor atoms here for our ligands. And the number of donor atoms that bond directly to the metal is what's known as its coordination number. Now, there are certain ligands that are what are referred to as being monodentate, which means they can bind in basically one place per molecule. So, like water here, when it hooks up with a metal, will pretty much just bond through the oxygen in one spot. Same thing with the nitrogen here, say in NH3, when it sort of bonds to the metal there in the middle, it's going to just bond in one spot. Now, there's also ligands that are what are referred to as being bidentate, ethyl endyl diamine, which is oftentimes abbreviated with an EN. Looks something like this. I'll give it a go. Why not? Do a little bit of that, a little bit of this, and a little bit of this, perhaps. A little bit of dots there, a little bit of dots there. This is ethyl endyl diamine, or EN. And when it goes to attach to a metal ion, it's able to do so through both of the nitrogens that are attached to it. So when you think about coordination number, you get a 2-for-1 deal on that. So for every molecule of EN that binds in there, you get basically 2 attachments. If we had 2 of these guys, for example, we would have a coordination number of 1, 2, 3, and 4 would be our coordination number in this case, as opposed to if we were just looking at this guy, that would provide 1, this would provide 1, and this would be a coordination number of 2 in this case, as those each only bind in one place if we bound those 2 guys to a metal. Another very common, I would say, bidentate ligand is oxalate. And I think I might have drew it in an earlier chapter, but once again, this is what oxalate looks like if you draw it. And at each of these single bonded oxygens, it has the ability to attach to a metal. So it also gives a 2-for-1 type of situation in terms of the coordination number. I would say oxalate and ethyl endyl diamine are 2 of the most common bidentate ligands that you come across, and it does affect the coordination number. Now, if we look at something, there's also ligands that are crazy enough that they actually bind in several locations. EDTA can bind in like 6 different locations per molecule. So there's a lot of places where it can really grab onto a metal. As we'll talk about it, sometimes that's referred to as a metal chelator because it basically just surrounds the metal and encompasses it per molecule because it binds it up pretty well. Any questions on that there? So when we look back at, for example, the one that we saw here, just to finish up on this guy here, each of these ligands here are all monodentate, which means all the nitrogens here are going to be the atom binding to the metal. The Cl is the atom to bind the metal. So in this case, the coordination number here would be 6 for this guy, as that is basically how many that you have attached to it. Now, it's not always going to be, for example, if you look at a complex ion, something like this, it will not always be like the little number on the bottom there in the formula. It will be if it's monodentate, but if you have some bidentate in there, it will not always be the little subscript on the bottom. So sometimes people always think it's like the little subscript on the bottom of the formula. It would be the coordination number, but it does depend on the type of ligand that you have going on there. Any questions on that there? All right, we'll lay it up there for today.